Hi, Professor. So I did my literature assignment on the nucleophilic aromatic substitution paper. So first off, the molecular target was the anti-cancer drug RS bicalutamide. And then that's a non-steroid anti-androgen. An anti-androgen is, it blocks androgens from binding to androgen receptors in prostate cancer cells. So it essentially starves the cells of the androgens that's required for it to grow. However, it doesn't actually stop androgen production. So it's the leading non-steroid anti-androgen explicitly for treatment of prostate cancer. So those are its biological properties. Other key information is it's sold under the name Casodex. And before this method, there are two previously reported synthesis methods. However, they required more expensive starting materials and had a lower percent yield. So there is one stereocenter in this molecule. And I will share my screen to show you because I have marked it. If I can get this to, there we go. So this right here is the end product. So right here, this is the one stereocenter in the molecule. So some key transformations that are used to construct the molecule include, as previously stated, nucleophilic aromatic substitution, as well as epoxidation, the opening of an epoxide ring, and oxidation. So an explanation of scheme 1 plus the intermediates for each synthetic step. So first of all, right here, this is going to be our first intermediate. So in the reaction, so first of all, fluorine is going to be the most reactive because it's more electronegative. And that's because the fluorine pulls so much electron density that there's a big buildup of positive charge at its position, which is what allows for the nucleophilic aromatic substitution. And that's going to happen through the creation of the benzyne as an intermediate, which is where we get this right here. And then after this, structure 4, it undergoes epoxidation. And it does this because it's a base in the presence of hydrogen peroxide. Well, sorry. It forms an epoxide because this is an electrophilic alkene. So it's an alpha beta unsaturated carbonyl. And therefore, you can't use MCPBA to perform epoxidation. So a base in the presence of hydrogen peroxide is added to do that. And then after that structure is formed, there is an epoxide ring opening that occurs via a sulfide bonding. And then after the sulfide bonds, there is an oxidation of the sulfide to get the final product. And the final product is this right here. So this is the sulfide that has to be oxidized. And then this right here is what is added to open up the epoxide ring. So another key intermediate is right after the ring is opened, after the epoxide ring is opened. So this is the structure right after the epoxide ring is opened, before the sulfur is oxidized. So this is the second key transition state. The mechanism. So the full mechanism for steps 2 through 4 is right here. So I did this through ChemDraw. So first off, we have our two starting materials right here. So the lone pair on the nitrogen attacks this hydrogen right here, causing the hydrogen bond to break and leaving a negative charge right here. The negative charge goes here towards this double bond, causing the fluorine, which is very electronegative and a very good leaving group, to leave. So at this point also, we'll have an NH3 right here, and this still has to add on at some point to the, how do you say? It still has to add on to the structure right here. So in the reagents, they also added NaH, which is a very strong base. It's not a good nucleophile, but it's a very strong base. And its chief purpose is for deprotonation. So it deprotonates this NH bond right here because this nitrogen has a positive charge, leaving it with NH2. So we get right here, and this has the NH2 with the lone pair again, and we have sodium and the H2 ion. And then at this point, we also have the benzyne ring. So the lone pair and the nitrogen attacks right here, which is where the fluorine was, causing this triple bond to go back to this carbon. And then finally, well, not finally, but next, and then this leaves a negative charge right here. And then we have this synthesis here where this is added in, well, substituted in the place of the fluorine. The negative charge attacks the now positive nitrogen with this extra hydrogen. So it takes this hydrogen right here, and this hydrogen bond rebounds, and then we get our final, well, not our final product, but we get our next step in the reaction, which is step 4. So right here, this is step 4. So let me stop my screen sharing. A reaction that I was pretty unfamiliar with. So there was an immediate deprotonation of the aryl amide proton in structure 4 mentioned in the paper. And I had to read up on that a bit because that definitely confused me because that wasn't something that I was really aware of. And then, so it was an immediate deprotonation by the excess base after it formed. And therefore it deactivated the alpha beta unsaturated carbon-carbon double bond. So that prevented nucleophilic addition from occurring. But I didn't think that in this type of reaction, in what we've done in class, I didn't think that nucleophilic addition was really possible, I guess. So that's why I was confused, because this immediate deprotonation occurred to prevent this, but I guess I didn't know that that was how that went about in terms of why substitution happens over addition. So that was really cool for me to learn. And then I guess my final reflection. So I was probably most surprised with the difference in the percent yield of the drug from the previous methods of synthesis, which was 50 to 70%. So it's decent, but not the best. And the fact that this method of synthesis has a 97% yield rate, that difference was crazy to me. I also didn't expect the yield for this method of synthesis to be so high, because in experimental settings, I don't know, I've always experienced whenever we've done things with percent yield, actually in the lab, the percent yield has just never been that close to 100 before. So that was really cool. And then I think that the most confusing thing to me was the fact that the NaH that was added to make the reaction go smoother and eventually take that hydrogen off of the NH3 that formed so that the so that it could become NH2 to bond. The fact that there was a 2.6 equivalent of that added. So I understand that NaH allowed the reaction to occur, but why was 2.6 equivalent necessary? It just feels very specific. I would expect 1 or 2 or 1.5, but 2.6. That's just a very specific amount. So that was something that that was a little confusing to me too, because I didn't understand why you would need that specific amount. But yeah, that was my literature assignment. Thank you so much.